So this question deals with kinetics for specifically a first order reaction for a cis-retinal. We're told some given information about the reaction, but the most important piece of information we have is that it's first order. So we have the first order rate law expression written right here, that if we have the negative log of concentration of our reactant here at a certain time and we subtract the original starting concentration, that's what the A sub 0 represents. If we subtract the negative log of that concentration, it equals the negative of the time that's elapsed times the rate constant for that first order reaction. Now here's the relevant information that we're given. We're given the value of the rate constant K. We're given the amount of time that elapses in hours, so it's going to be 6.00 hours, and we're given the starting concentration A sub 0 of the cis-retinal here, 3.5 times 10 to the negative 3 molar. Here's what we want to solve for, the concentration after 6 hours has elapsed. So let's plug into the formula all the information we're given for part A. Now in solving this, since this first term is what we want to solve for, I'm going to go ahead and add the natural log term over here to this side of the reaction. Okay, so that just kind of gives us the appropriate information that we're solving for exclusively on the left side. And now let's plug in what we know, starting with the negative KT term. So negative of the rate constant is the first term. And now we need our time element. And I always like to put units in when we do calculations because then it's easy to catch mistakes. You see, the units of the rate constant are given in seconds or inverse seconds, but our time element is in hours. So we're going to need to, before we can put in the time element t here, convert it first to seconds. So here's our conversion factor. If we have 6 hours and there are 3,600 seconds in an hour, that converts to 21,600 seconds. Now, because our first number, k, is already in scientific notation, let's go ahead and put the time element in scientific notation as well to give 2.16 times 10 to the fourth seconds. It's the same as this number, but just in scientific notation. And then we add natural log of our starting concentration, which was the natural log of that 3.5 times 10 to the negative 3 molar. So let's go ahead and figure out this product and the natural log of this term and add them together and see what we come up with. So negative 0.220 is what we get for our initial product. Natural log term gives us negative 5.65. We add those two together, we get a negative 5.87, which is equal to that natural log of the concentration at time t. So we're going to take now the inverse natural log of that negative 5.87 term to ultimately give us then the concentration at time t. So when we go ahead and take that inverse natural log, we get the answer to the question, which is 0.00282. Let me just fix that. Looks a little weird. Molar in terms of the concentration that still remains after that 6-hour time frame. Part B of this question asks us to determine the time frame needed to react away 25% of our reactant. So there's a couple ways we can approach this question, but one of the ways that probably makes the most sense is to just go back to some of the information we had in the first part of the question, which is we know the rate constant, we know the equation we need to use. We know that this concentration right here is the amount that remains after time t. So if we react away 25%, 75% would still be remaining at time t. So let's take 75% of a starting concentration and call that the concentration that remains at time t. So this version of the calculation is probably the easiest to work with. We can have the starting concentration be whatever we want it to be because we're just going to deal with 75% of whatever that amount is. So let's just have the starting concentration be a nice easy number like 1 molar. So 75% of that is going to be 0.75 molar. Those are the numbers we're going to plug in for concentrations. Again, we have the value for K that was given above. So now all we have to do is take the difference between these two natural log values, where the concentration, again, are 0.75 and 1 molar respectively, and divide by negative K to get the time that's elapsed. So if we modify the equation plugging in what we know, we're taking the natural log of 0.75 minus the natural log of 1 times the negative of our rate constant. We're going to divide both sides then by that negative K value once we determine the difference between those natural logs, and that'll give us our time. And the units of time, remember, are consistent with the units of the rate constant. They're going to be in seconds. So we complete the math here. Natural log of 1 is always going to just be 0. So we get a negative 0.29, and we divide that by that K term, and that's going to give us 28,000 seconds. It does ask us to represent the answer in terms of minutes, though, so 60 seconds per minute. Do that final conversion and divide the seconds by 60, and we get 470 minutes. So that's the answer to part B. So we have one final part. So part C, the final part, just is the same equation that we've been using. This time, the concentration that we want to have remaining after a certain amount of time is 3.15 times 10 to the negative 3. So we're going to plug that in for A at time t. Our initial concentration, we go back to what they gave us in part A, the 3.5 times 10 to the negative 3. Here's our rate constant. Time t, this time they want it to be in hours, is what we're solving for. So again, we'll take the difference between these two natural log terms, divide by the negative of that rate constant, and that should give us our time. So when we complete that part, we get 11,000 seconds for time t, but again, they ask for it in terms of hours, so 3,600 seconds in an hour. We divide that by 3,600, we get 3.00 hours.